Two people walk into a research lab on their 45th birthday. Same calendar age, same number of years lived. But when scientists measure their biology, something strange appears. One person's cells, cardiovascular system, and metabolic markers look 42. The others look 58. A 16-year biological difference between two people born on the same day. In population studies tracking thousands of people through midlife, researchers consistently see this pattern. Bodies diverge. Some people's biology ages at what appears to be the expected rate, others age significantly faster, and a small percentage age noticeably slower. This video explores one question: when does this biological fork appear? And what causes some people's biology to take one path while others take another? The answer reveals itself through 5 specific markers. Let's start with the one that appears earliest. The first marker appears in how bodies transition from sleep to waking. In studies tracking thousands of people in their 40s, researchers found a curious split. Some participants woke up and moved immediately, no warm-up needed. Their bodies transitioned from sleep to activity seamlessly. Others reported needing 20 to 30 minutes to loosen up. Movement felt restricted, particularly in lower back, hips, and shoulders. They described getting out of bed carefully, moving slowly at first, then gradually feeling normal again. Same age group, dramatically different morning experience. The difference appears to be in connective tissue hydration. Think of your connective tissue, fascia, tendons, ligaments, like a network of elastic bands. In some bodies, this network maintains its elasticity overnight. The person wakes up, the tissue is ready for movement. In other bodies, the tissue loses water content during sleep hours. It becomes temporarily rigid. Movement gradually rehydrates it back to flexibility. This is driven by a molecule called hyaluronic acid, which helps tissue retain water. Here's what's fascinating. In your 20s and 30s, most people produce hyaluronic acid abundantly. Nearly everyone wakes up flexible. But starting around age 40, production begins to diverge dramatically. Some people at 45 still produce it at levels similar to age 35. Others at 45 are producing it at levels typical of age 55 or 60. The gap widens, and morning tissue stiffness becomes a measurable marker of this divergence. The second marker appears in what researchers call diurnal facial changes, how faces change from morning to afternoon. In a fascinating 2019 study, researchers photographed people's faces at 8 a.m. and again at 4 p.m., then measured structural differences. Some participants' faces looked essentially identical between morning and afternoon. The structure held stable throughout the day. Others showed noticeable changes by mid-afternoon. Skin appeared less taut, lines became more pronounced, facial contours seemed to shift slightly downward. What's causing this real-time visible difference? The answer lies in collagen scaffolding. Your skin sits on top of a structural framework made primarily of collagen and elastin. Imagine it like the framework holding up a tent. In some people, this scaffolding maintains its structural integrity throughout the day. Morning and afternoon look the same because the framework is holding firm against gravity's constant downward pull. In others, the scaffolding shows strain by mid-afternoon. After 6 to 8 hours of gravity pulling on weakened structure, the strain becomes visible. You're watching real-time evidence of how well the collagen network is maintaining itself. And here's what makes this particularly interesting. The rate of afternoon change correlates strongly with overall collagen production rates. In populations studied, people showing minimal diurnal change had collagen production rates similar to people 5 to 10 years younger. People showing significant diurnal change had collagen production rates similar to people 10 to 15 years older. Same calendar age, different collagen biology. The third marker appears somewhere unexpected: gum tissue. In longitudinal studies following people from age 35 to 50, researchers noticed a striking pattern. Some participants maintained stable gum lines throughout this 15-year period. Minimal recession, teeth looked the same size. Others showed progressive gum recession. Over the same 15 years, their gums pulled back noticeably. More tooth root became exposed. Some reported increased sensitivity. Why would gum tissue behavior vary so dramatically between people of the same age? The answer connects to something happening beneath the gums: bone remodeling rates. Your gums sit on top of jawbone. That bone is alive, constantly being broken down and rebuilt in a careful balance. When breakdown and rebuilding happen at similar rates, gum tissue stays stable. But when breakdown accelerates while rebuilding slows, the jawbone begins to recede. The gum tissue, having nothing to hold on to, follows the bone downward. Here's what makes this such a valuable marker. Jawbone behavior tends to mirror what's happening throughout the entire skeleton. In the same longitudinal studies, researchers found that people with significant gum recession showed measurably different bone density patterns in hips, spine, and wrists compared to people with stable gums, even at the same calendar age. Your jawbone is essentially broadcasting a signal about your skeletal system's overall remodeling balance. The fourth marker shows up in temperature regulation. In climate-controlled lab studies, researchers made a curious observation. They set room temperature at 72 degrees Fahrenheit, 22 degrees Celsius, typically considered comfortable, and tracked participants' thermal comfort. Some participants at age 45 reported feeling comfortable, just as they did at age 35. Others at age 45 reported feeling too cold or too hot in the same environment that had felt comfortable to them a decade earlier. Their comfortable temperature range had narrowed significantly. What's driving this divergence? The mechanism appears to be vascular responsiveness, specifically how precisely blood vessels near your skin surface can dilate and constrict. Your body maintains temperature through blood flow modulation. Too warm, vessels near skin surface dilate. More blood flows near surface, heat radiates away. Too cold, vessels constrict. Less blood flows near surface, heat stays in your core. This system requires extraordinarily precise control, moment-to-moment adjustments based on environmental feedback. In some people through midlife, this precision holds steady. Vessels respond accurately to small temperature changes. The comfortable range stays wide. In others, the system becomes less precise. Vessels overreact or underreact. They miss small changes and then overcorrect when they finally respond. This appears to correlate with changes in the endothelium, the inner lining of blood vessels that acts as the control surface for dilation and constriction. And here's what surprised researchers. Temperature comfort range narrowing often appears 3 to 5 years before other cardiovascular markers show changes. It's an early signal of vascular aging that most people never connect to their cardiovascular system. The fifth marker appears in recovery time from physical exertion. In exercise physiology studies, researchers give people of the same age identical strength challenges, say a standardized strength workout, then track recovery. Here's what they consistently find. Some participants at age 45 recovered to baseline within 24 hours. They report feeling back to normal the next day. Others from the same age group require 48 to 72 hours to reach the same baseline. Some report lingering soreness for 3 to 4 days. Why such dramatic variation in response to identical challenge? The answer appears to be cellular repair efficiency, specifically how quickly cells can clear damage and rebuild tissue after exertion.
When you exert yourself physically, you create microscopic damage in muscle fibers. This is normal and necessary. Recovery requires your cells to remove damaged proteins, clear inflammatory byproducts, rebuild tissue with new proteins, and restore energy reserves. In some people, this entire process runs efficiently. Damage cleared quickly, tissue rebuilt promptly, 24-hour recovery. In others, every step runs slower. Damaged proteins linger, inflammatory signals stay active longer, rebuilding takes more time, 72-hour recovery. What's fascinating, recovery time turns out to be one of the most accurate single predictors of biological age. In studies comparing recovery time to comprehensive biological testing, the correlation was remarkable. People recovering in 24 hours showed biological markers of someone 5 to 10 years younger than their calendar age. People requiring 72 hours showed markers of someone 10 to 15 years older.
You might be wondering, why do these 5 markers appear together? Because they all trace back to one underlying biological system that starts diverging in midlife. That system is cellular energy efficiency. Not how much energy you have, how efficiently your cells convert resources into usable energy. Think of it like 2 factories processing the same raw materials. One factory has modern, efficient machinery. Every unit of input produces maximum output, minimal waste. The other factory has older, less efficient machinery. Same input, but lower output, more waste generated. That's what's happening at the cellular level. In some people, cellular energy conversion stays efficient through midlife. Their cells extract and use energy from nutrients effectively. In others, conversion efficiency declines. The cellular machinery becomes less efficient, more resources required to produce the same energy output. And here's why this matters for all 5 markers. Marker number 1, morning stiffness. Connective tissue repair requires energy. Efficient cells maintain tissue better. Less efficient cells, slower tissue maintenance. Morning stiffness increases. Marker number 2, facial changes. Collagen production is energy intensive. Efficient cells, robust collagen production, stable structure. Less efficient, reduced production, visible strain. Marker number 3, gum recession. Bone remodeling requires enormous energy. Efficient cells, balanced remodeling. Less efficient, imbalanced process, recession. Marker number 4, temperature regulation. Vascular control requires constant micro-adjustments. Efficient cells, precise control. Less efficient, imprecise, delayed responses. Marker number 5, recovery time. Cellular repair is the most energy-demanding process. Efficient cells, fast recovery. Less efficient, extended recovery. It all connects through cellular energy efficiency. But this raises the obvious question, what causes efficiency to diverge in the first place? Here's what researchers have discovered about why cellular energy efficiency diverges in midlife. Your cells have quality control systems that monitor the machinery responsible for energy production. When machinery starts wearing out or performing poorly, quality control systems are supposed to mark it for removal and trigger production of new replacement machinery. This process is called mitophagy and biogenesis, the removal of inefficient cellular machinery and creation of new efficient machinery. In your 20s and 30s, this quality control operates robustly. Worn machinery removed promptly, new machinery produced consistently. Energy efficiency stays high. But starting around age 40, something interesting happens. The quality control system itself begins to slow down. Not in everyone at the same rate, that's the key. In some people, quality control continues operating effectively through midlife. They continue removing inefficient machinery and producing new, efficient replacements. Their cellular energy efficiency holds steady.
In others, quality control starts missing things. Worn machinery stays in place longer. Production of new machinery slows. Gradually, their cellular fleet becomes less efficient. Same age, different quality control effectiveness. And here's what makes this divergence particularly important. It's highly responsive to environmental signals.
The cellular quality control system operates based on signals it receives about demand. When you regularly challenge your body, when you ask your muscles to do hard things, you send strong signals. We need efficient energy production. Maintain the machinery. When you don't challenge your body regularly, the signals weaken. Energy demand is low. No need to invest resources in maintaining peak efficiency. Your cells adapt to the environment you create. Here's what makes the biological fork feel like it happens suddenly. There's a long, silent period where cellular efficiency is declining, but you don't notice any effects. Then, seemingly overnight, all 5 markers appear at once. Why the gap? Because your body has reserve capacity. Think of it like a power grid designed to handle 100 units of demand, but currently only using 60 units. Early cellular efficiency decline might drop you from 100 capacity to 90, then 85, then 80. But you're still only using 60 units, so you notice nothing. All systems run normally. Then, one day you cross below 70. Now your capacity is getting close to your daily demand. Things start feeling different. And once you hit 65, suddenly everything becomes noticeable. Morning stiffness appears, afternoon face changes, temperature sensitivity, recovery time extends. It feels sudden because you crossed the visibility threshold, but the decline was happening silently for 5 to 7 years. This is the pattern researchers see consistently: long, invisible period, then rapid visibility. But there's a critical phase in this process that determines everything that comes next. In longitudinal studies tracking people across midlife, researchers noticed something striking.
There's a point where biological divergence accelerates, where the gap between efficient and less efficient widens dramatically. They call this the inflection point. Before the inflection point, cellular efficiency decline is relatively linear. You lose a bit each year, but it's predictable. After the inflection point, something changes. The decline becomes self-accelerating. Here's why. When cellular efficiency drops below approximately 70% of original capacity, you no longer have enough energy for optimal repair and maintenance. So damage starts accumulating faster than you can clear it. Accumulated damage creates oxidative stress. Oxidative stress damages more cellular machinery. More damaged machinery means even lower efficiency. Lower efficiency means even less energy for repair, which allows even more damage to accumulate. It becomes a self-reinforcing cycle. Researchers estimate the inflection point hits at different calendar ages for different people. Some people reach it at 42, others not until 52. The difference appears to be how much reserve capacity they maintained through their 30s and early 40s. Here's the encouraging part of this biological pattern. Before the inflection point, the cellular quality control system remains highly responsive to environmental signals. Remember, the system operates based on demand signals it receives. In studies where people increased physical challenge after years of low activity, researchers found something remarkable. Within 3 to 6 months, cellular quality control systems showed measurable improvement. More efficient machinery being produced, less efficient machinery being removed more promptly. Within 6 to 12 months, the 5 divergence markers began shifting. Morning tissue stiffness duration decreased. Collagen production markers improved. Bone remodeling ratios moved toward balance. Vascular responsiveness enhanced. Recovery time shortened. But here's what makes timing critical.
This responsiveness appears to decrease significantly after the inflection point. Before the inflection point, you're working with a system that can still ramp up efficiently, change the signals, get a response. After the inflection point, you're working against momentum. The self-reinforcing cycle has started. You can still improve, but it requires more sustained effort over longer time periods. By age 50, population studies show a clear split pattern. Group A, approximately 30%, people whose cellular efficiency remained high through midlife. Their 5 markers stay minimal, morning flexibility maintained, facial structure stable, gum lines unchanged, temperature comfort wide, recovery rapid. Group B, approximately 40%, people in the middle of the spectrum, showing 2 to 3 markers moderately, some morning stiffness, slight afternoon changes, moderate temperature sensitivity, recovery taking 36 to 48 hours instead of 24. Group C, people whose efficiency declined significantly, showing all 5 markers noticeably, extended morning stiffness, clear facial changes, visible gum recession, narrow temperature comfort, recovery requiring 72+ hours. What determines which group someone lands in? The research points to 3 primary environmental factors. Factor 1, physical challenge patterns through 30s and 40s, not just activity, challenge, regular signals that demand efficient energy production. Factor 2, sleep quality, not duration, quality. Deep sleep stages are when quality control systems do their most intensive work. Factor 3, metabolic stress load, chronic inflammation, oxidative stress from diet and environment. These interfere with quality control efficiency. What's encouraging, none of these are genetic destiny. They're environmental signals, which means the split isn't predetermined, it's responsive.
This video explored one question. When does the biological fork appear? And what causes some people's biology to take one path while others take another? The answer? Starting around age 40, cellular energy efficiency begins to diverge between people. Some maintain high efficiency through midlife. Others experience decline at varying rates. This divergence becomes visible through 5 measurable markers: morning tissue flexibility patterns, diurnal structural stability, skeletal remodeling signals, thermal regulatory range, cellular repair rates. Each marker traces back to the same underlying system: how efficiently cells convert resources into usable energy. The fork appears when cellular quality control, the system maintaining efficient machinery, begins operating differently in different people based on the environmental signals they receive. For some, quality control stays robust. For others, it slows. And this creates the 16-year biological age gap we opened with. 2 people born the same day, but their cellular biology has taken different paths. But here's what makes this pattern genuinely important to understand. The fork isn't genetic destiny, it's environmental response. Your cells are constantly receiving signals about what level of efficiency they need to maintain. They're reading the environment you create, the physical challenges you present, the sleep quality you provide, the metabolic stress you manage, and they're adapting accordingly. The 5 markers aren't warnings of inevitable decline, they're feedback, real-time information about what state your cellular quality control is currently in. Some people see this feedback in their early 40s, while their response window is still wide. Others don't notice until later, when the inflection point has already been crossed. But whenever it appears, it's showing up because something measurable is happening underneath, something responsive. Most people experiencing these markers think, "I'm just getting older, this is normal." But these aren't markers of inevitable aging. They're markers of adaptive aging, your biology responding to the signals it's been receiving.
That's what this channel explores, the biological transitions happening between 30 and 60 that most people experience without understanding what's actually changing, the invisible forks that appear, the systems that diverge, the feedback signals appearing while you can still respond. Because biological aging isn't a straight line, it's not inevitable decline at a fixed rate for everyone. It's a series of divergence points where your biology can take different paths based on the signals it receives. The fork appeared. Now you know what it looks like and what's causing it to point the direction it's currently pointing.